Somewhere in our galaxy, there is a star so large that if you placed it where our Sun is right now, it would swallow Mercury, Venus, Earth, Mars, Jupiter, and keep going all the way to Saturn before its edge finally runs out of sky. It is also one of the coldest stars we know, and that is exactly why it got this big. And according to our best understanding of how stars work, it shouldn't exist. It's called Stephenson 2-18, the largest star we have ever found. More than 2,000 times wider than our Sun. Not the brightest, not the hottest, enormous precisely because it has been cooling for millions of years. Its outer layers expanding outward slowly as the star aged into something almost unrecognizable from what it once was. But the deeper you go into what we actually know about this star, the stranger it gets, because at some point the measurements stop making sense. And what they reveal isn't just a big star, it's a question our physics hasn't answered yet. Stephenson 2-18 sits roughly 19,000 light-years from Earth in the constellation Scutum, buried deep behind interstellar dust near the inner arm of the Milky Way. So far away that the light reaching us now left the star before the first cave paintings existed. It's a red supergiant, the kind of star that only exists when something massive has been burning for millions of years and is starting to come undone. Two questions I want you to hold on to as we go. How does something get this big? And what does it mean that our current models of stellar physics say the size we measured is impossible? Both answers are stranger than I expected. In 1990, an American astronomer named Charles Bruce Stephenson was mapping distant star clusters in the Milky Way. He found a loose grouping of massive, aging stars. The cluster took his name. Stephenson 2. One star in that region barely got a number. Object 18, ST2-18. Nobody paid it much attention. For decades, the title of largest known star passed between other giants. VY Canis Majoris, then UY Scuti, then others. Every few years, new measurements, new analyses. The crown moved again and again, and then astronomers looked more carefully at Object 18, a star that had been sitting in a catalogue with a number instead of a name. When they studied it in depth in 2012, the number that came back stopped them cold. More than 2,150 times the width of our Sun. Nothing else came close. And as far as we know today, nothing still does. The largest thing in the known universe had been filed away under a number. Waiting. We are genuinely terrible at understanding scale. Our brains were built for savannas, not solar systems. So let's start somewhere familiar. Our Sun is 1.4 million kilometers wide. That's not a typo. If you drove a car at motorway speed without stopping, it would take you 170 years to cross it. Stephenson 2-18 is more than 2,150 times wider than that. If the Sun were a golf ball, Stephenson 2-18 would be the height of the Empire State Building. Every planet, every moon, every asteroid between here and Saturn. Inside, and somewhere inside that incomprehensible volume of star, you and I and everything we've ever known would fit without leaving a trace. Light travels at 300,000 kilometers per second. It crosses the full diameter of our Sun in about 4.6 seconds. Roughly the time it takes to read this sentence aloud. To travel around the circumference of Stephenson 2-18 at that same speed, nearly 9 hours, the same amount of time most people sleep. A transatlantic flight, round trip with time to spare. One loop around the surface of a single star. Light. The fastest thing in the universe. Takes most of a working day to go around it once. But that's not the craziest part. Here's the thing that stopped me when I first went deep on this star. Stars have colors. And color tells you temperature. The hottest stars burn blue-white like an arc welder. Our sun is yellow-white, middling. Cool stars glow red. Stephenson 218 is deep red. Its surface sits at around 3,200 degrees Celsius. Our sun burns at nearly 5,800. The most extreme stars in the universe reach 40,000 or more. This star, the largest we've ever found, runs cooler than a welding flame. And that is not a coincidence. It got bigger precisely because it cooled. As the outer layers of a massive star lose heat, they lose the pressure holding them inward. They expand outward. Slowly at first, then dramatically over millions of years. The biggest thing we've ever found is big because it's been slowly dying. It inflated as it aged. The way an ember glows widest just before it goes dark. You'd expect the largest star to be the most ferocious. It turns out size and fury have nothing to do with each other, and that quiet inversion. A star growing vast precisely by cooling, by losing its grip, is already the first place where our models start to struggle with what they're looking at. For all its cooling, this star is not at rest. Stephenson 218 radiates as much energy as roughly 440,000 of our suns combined. By the time I finish this sentence, this star has released more energy than our sun will produce in the next several thousand years. Our sun has been burning for 4.6 billion years, what it generates over several hundred million of those years. Stephenson 218 pours out in 12 months, and it does this every year, hemorrhaging energy it cannot sustain indefinitely. It is the brightest slow death imaginable. So how does something get this big? It starts in a molecular cloud, a region of space so vast and so cold it barely qualifies as matter. Hydrogen gas and dust drifting for millions of years, no particular destination. The cloud that eventually became this star was likely wider than the distance between our sun and its nearest neighbor. Just gas, patient. The universe has time in ways we don't. But here's where it gets strange. At some point, nudged by the shockwave of a nearby explosion, or simply by its own slow accumulation, the cloud begins to collapse inward. The core heats up, the pressure climbs, and at some threshold, the hydrogen ignites. A star wakes up. At that point, it was probably 15 to 25 times more massive than our sun. Compact, blazing, nothing like what we see today. Over millions of years, it burned through its hydrogen. The outward push of energy from the core weakened. The outer layers, vast, cooling, began to drift outward, slowly becoming the swollen, dimly glowing shape we now observe. What its mass is today. After millions of years of shedding material into space through powerful outward flows from its surface, is genuinely unknown. We know the size, we don't know the weight, and that missing number turns out to matter more than you'd expect. Because when you add it all up, the size, the temperature, the way it formed, you get something that sits just outside the edge of what our physics says should be possible. Here's something the numbers alone don't tell you. The star is so far away, so embedded in the dust-choked interior of the Milky Way, that the distance measurement carries an uncertainty of over 50%. And the radius, more than 2,150 times the width of our sun, is calculated directly from that distance. If the distance is wrong, everything else is wrong too. Some researchers believe ST2-18 might not even belong to the Stephenson 2 cluster at all. It could be a foreground star at a completely different distance. Closer than we think, or farther. The name implies membership. The data doesn't fully confirm it, which means the largest star we've ever catalogued might be filed under the wrong address. And here's what I find genuinely unsettling about this. There could be larger stars hiding behind that dust right now. Objects we haven't measured. Objects our current telescopes can't fully reach through the haze of the inner galaxy. Every answer about this star comes with a quiet asterisk attached. At some point, and in cosmic terms, that could mean tomorrow or 100,000 years from now. Stephenson 218 will run out of fuel it can burn in its core. When that happens, the core collapses in a fraction of a second. The outer layers come crashing inward, then rebound outward in a single catastrophic instant. The energy released in that moment is almost incomprehensible. For a few weeks, one dying star can outshine an entire galaxy containing hundreds of billions of other stars. From Earth, 19,000 light-years away, we would likely see a new point of light appear in the sky, bright enough to be visible in full daylight, visible for weeks, perhaps months. What's left behind would be either a neutron star, an object the size of a city but heavier than our Sun, or, if enough mass remains in the core, a black hole, a city-sized remnant, or an invisible gravitational trap. The same matter that once swallowed everything between here and Saturn, compressed into something you could drive across in an hour. But here's what I keep landing on, and it has nothing to do with the size itself. Our best models of how stars live and die, built from decades of observation, mathematics, and physics, predict a ceiling, a maximum size that a red supergiant can physically reach before the outward push of its own energy tears it apart rather than letting it expand further. That ceiling sits at around 1,500 times the width of our Sun. Stephenson 2-18 measures more than 2,150. That's not a rounding error. That's 40% beyond the theoretical limit, which means one of two things has to be true, and they're unsettling in completely different ways. Either we measured the star wrong, the distance estimate is off, the size calculation is flawed, and the real number is smaller than we think. In which case, we've been calling something the largest star in the known universe for years, and it may not deserve the title. The throne could belong to something else, or to nothing we've found yet. Or the physics is wrong. Our models have a gap. Something we don't yet understand about how the most massive stars behave in the final stages of their lives. And if that's true, then everything we predict about how stars like this die when they explode and what they leave behind is built on a foundation with a crack running through it. We don't know which it is, and right now, nobody has resolved it. The largest object we have ever found in the universe, and we cannot say with certainty whether it is a measurement error or a hole in our understanding of physics. That is the honest answer. The light we're seeing left 19,000 years ago. It might already be dead.